Hello, hello. Okay, so yeah, I didn't stream for a long time, close to 2 weeks. Yeah, was sick last week. So checking the stream. Yeah, looks like it started. I still do not see it yet. Let me check on this screen. Okay. Okay, so we are up and running, which is really good. Okay, so yeah, I've decided to change a little bit on the structure of the stream. So instead of like only coding like random problems, I would start focusing more on some specific problems, mainly some specific topic. So for this topic of this session, I'll be coding mainly and trying to solve mainly easy problems, still easy problems, though they will be more like with a specific tag. So in our case, our tag it's bit manipulation. So yeah, let's go one by one and solve everything which we can find on bit manipulation. Yeah, so first problem. Count consistent strings. Okay, so let me check if everything looks good. Again. Okay, cool. Maybe I can zoom it a little bit more even. Yeah. Let me zoom it here. Checking the stream health. Yeah, everything is awesome. Cool. Yeah, so what's this about? You're given a string allowed consisting of distinct characters and an array of string words. A string is consistent if all characters in the string appear in the string allowed. Okay, so return the number of consistent strings in array words. So we have like AB and words AD, BD, AAB, BA, BD, AAB. So strings AAB and BA are consistent since they only contain characters A and B. ABC, yeah, that's an interesting one because I am not sure how exactly this it's bit oriented. So it's a hash table string bit manipulation. So yeah, let's check the hints. A string is incorrect if it contains a character that is not allowed. Yeah, makes sense. Contains are small enough for brute force. Okay, so by brute force, what does it really mean? Like having going through all letters in every word and checking if those letters are existent, are allowed. That's the idea. Yeah, probably we'll code it like this. Yeah, so let's try to code it in this way. So we have allowed, which is in a string form. I'm not sure if it contains, I think, so two. Okay, so what do we need to count first? Return the number of consistent strings in array words. Consistent strings. Okay, so we need to count the number of words. Okay. Yeah. Okay. So words. We'll have an iterator. Then we'll filter them. So each word. So we'll have each word here. And for letters, we can do like allowed, chars, every, I think, every. And here we'll apply, or all, I think it's all. We need to check char, ch, what contains ch. And then we do a count and as I32. Yeah, kind of weird how this is a bit manipulation. Yeah, first let's check if this works. Mismatch type. The returns the body. Okay, so we don't need to do this. Wrong answer. Okay. Expected 2, output 3, AB. Word contains GH. Yeah. All. Interesting one. Oh, it's not like that. Oh, we only need to have only letters which are allowed. So it should be like vice versa. Should be like not allowed chars, but word chars, and here allowed contains ch. So that should be the trick. Yeah, okay. So let's try to submit it. That's not a very fast solution. Though that's the good news about LeetCode. Once you solved it, you can check the results. Okay, so what this stuff? Okay. Allowed back. Okay, so it has a dictionary. Okay, so here he adds the letters or the characters in this dictionary in the allowed back. For in words. Okay, so for each word. Okay, so if it's there. Yeah, so he works with bytes, and this usually it's a little bit faster. But overall, it's same algorithm, because we have 2 for loops. So yeah, I've written this in a more pleasant way. So we have this first for loop with this filtering part, and then inside the second for loop for the words. So yeah, it's a little bit less efficient, but I like more this approach because it's easier to maintain, less code to write. So yeah, but overall memory it's good. So we are on memory, we are pretty good. Yeah. Solve this one. Flip an image. Yeah, let's check the next one. Flip and invert an image. Flip an image. Given an n by n binary matrix image, flip the image horizontally, then invert it and return the resulting image. To flip an image horizontally means that each row of the image is reversed. For example, flipping 1, 1, 0 horizontally results in 0, 1, 1. To invert an image means that each 0 is replaced by 1 and each 1 is replaced by 0. Okay. For example, inverting 0, 1, 1 results in 1, 0, 0. Okay, flip the image horizontally, then invert it. Okay. Second, I still don't understand why this is, or how this is bit manipulation. I mean, from one perspective, inverting a number 1 can become like this. So yeah, let's try this approach, because overall it's nothing fancy. We just need to flip, or to reverse, and then to invert, which it's pretty straightforward. Yeah. Let's try a simple example. Yeah, let me zoom this a little bit. So we'll be trying a simple example. Yeah. Dojo, cargo, new. Okay, let's call it example for now. Yeah, I'll not need the big one. I'll need the smaller one. Let me zoom it for you guys to see it better. Okay, so what I want to try, yeah, let's leave it as it is for now. What I want to try, it's inverting 1. So let A equal 1. Let B will be A. Print line B and A. Yeah, looks like I have a Copilot on. So usually I do not use Copilot on my training sessions. I use it for production more for production. Yeah. Okay, so let's try to run this part. So we have B will be -2. Oh. Why? It's B and A. Oh, it's not clear. Okay, so let's try this. Why it's a -1? Use perform bitwise not. Okay, so that's negation. But it's only for U8. Yeah, probably for I32 it works a little bit differently. A32. Yeah, let's try this. Oh, so this, it's A will be 0 and negation will be the max number. I think I started to understand what's the trouble with this approach. I need to write them in binary both. Yeah, so negation of 0 gives this amount. It's like that, yeah, A and B. Okay, so if I use a new 8, what will be in this case? Yeah, so still A will be 0 and 1. So how can we negate 0 as I32 to receive 1? A and B. Interesting. Not the XOR. This will not work. I guess we can do it for a simple for if statement. If it's 0, then it's 0. If it's 1, then 1. Yeah, okay. Images IJ is either 0 or 2. Yeah, we've got our constraints. So bit manipulation, matrix simulation. We don't have hints, nor do we need them. Yeah, let's try to code this and how we'll approach the result. So yeah, I guess simplest way to work on this as well, we'll create an iterator for the image and we'll receive yeah, the trick though is that we'll not be able to manipulate it, or will, yeah, maybe it will work. So we'll have a mapper function where we'll have like a row where we'll receive the entire row. Probably I'll do it like a mutable row. So we will do a row iterator, a mapper function, where if x 0, then 1, else 0. So that will be our mapper function, and we'll need to reverse it. Then we will collect, and we'll collect again here. So in theory, this should do the trick. Can't compare. Okay, so yeah, let's do it like this. Yeah, okay, so this seems like cryptic to some extent. To write this amount of code and for this to work right away. Great work. Oh, thank you, Kalinga. I would not even try to read the name. So welcome, Kalinga. Yeah, thank you for joining in. Yeah, if you have any specific questions, you can ask. We'll try to be as active as I can. Yeah, okay, so this now this reads a little bit better. Yeah, let me build it again if this works. Again, I don't understand how this is bit manipulation oriented. Yeah, maybe I've implemented it. Sri Lanka. Cool. Oh my God, that's the other the other part of the world. Sri Lanka. Yeah, I really want to visit Sri Lanka one day. because it's also that part of the world. Sri Lanka, maybe Myanmar, maybe even go to Vietnam and other places. Yeah, let's check another solution. Oh, look at here. This is how it's a bit oriented. So what does it do? To inverse a string, you just use XOR operator. Yeah, one day. So instead of this stuff, we can do x XOR 1, but you'll need to dereference this. So that will do the inverse. Yeah. So it's a little bit. Yeah. So he does manipulation on. Yeah, probably I did not use I'm using too much memory. So indeed, we don't need to do this. We can iterate mutably. But I don't understand how he reverses. So he reverses first and then does this. Reverses first and then does this. Okay, so if we do this, we don't need to collect. We don't need to collect here either. Yeah, so we can change this. I guess here will be just for each. So hover the row. Here for the row, we'll do the reverse part. And inside the row, we can do iterator. Again, mutably. And then we can do X. Yeah, we'll need to learn this pattern to change it. So don't we need to collect here? Map or for each again? I'm trying to rewrite this code to manipulate it inside. Yeah, let's see if this will work. I'm not sure. Okay, yeah, it's not right. Yeah, and probably here we'll need to do it like this. Okay. Can be used in a difference the left side. Okay, so yeah, they want to do reference. That's right. By the way, Kalinga, if I'm pronouncing your name correctly, how did you get? How did you get into to this channel? Did you learn Rust? What's up, guys? Hi, Jadel. J Cadell. Where are you from? Yeah, we'll need to make it mutable though. I guess that will do it. Yeah, I'm not sure. I mean, I like my first approach a little bit better, to be honest. Okay, so the reversing part looks like it doesn't work. Yeah, maybe we'll need to do mute. And maybe let's try a simple way. For x in row, x will be x. I'm DevOps. Yeah, probably Rust can be a good language for you to write some scripts. Oh, what? Oh, so we need to dereference it like this as well. Constantly hurrying Rust being adopted by Linux and Microsoft. Okay. Yeah, Rust, it's a very solid language. Yeah, I'm not sure if it did improve anything, but at least we did some bit manipulation. So my first approach, we use an if-else statement, but this it's a little bit better. Okay, so concerning Rust, it's a low-level language. It doesn't have a garbage collector. So once you pass the compiler, so as you will see a ton of time, I have like I need to dereference stuff, use addresses or references, pointers. So you need to get used to it because the syntax it's not straightforward. But once you get used to it, it's very powerful. So highly recommend to get into it. So at work, I'm also actually at work I do not use Rust. I'm a TypeScript developer, so writing Node.js, mainly backend. So we use Rust from time to time to optimize things, to write some native modules. Mainly I am doing this, but nothing heavily Rust oriented in our code base. Yeah. Jay, where are you from? So we have a Kalinga who is from Sri Lanka. Kalinga. By the way, I'm not sure. So Kalinga, so is it a male or a female name? I may be confused because my audience, yeah, used to know jazz as well. Yeah, so highly popular to have Node.js as a backend. Hi Jay. Yeah. So what we're doing here, we train Rust as well. We do we have a session of solving problems from LeetCode. So the topic of the day, it's a bit manipulation. Yeah, male. Okay. Yeah. Usually female names end with A. So that's a little bit confusing. So, but yeah, it's usually for us Europeans, or mainly from eastern part of Europe. So, okay. So I think we're done with this one. Flipping an image with its sum of subset XOR totals. Yeah, let's try this one. Okay. So what's up? Okay, so that should do it. Yeah, let's check this one. Yes, you are correct. Fine. Yeah, let's try to solve this one. The XOR or exclusive OR total of an array is defined as the bitwise XOR of all its elements, or 0 if the array is empty. For example, the total XOR total of the array 2, 5, 6 is 2 XOR 5 XOR 6 equal 1. Given an array nums, return the sum of all XOR totals for every subset of num. Wait, that's a little bit more interesting. Because we'll need to find subsets. Because, okay, so if we do all possible combination, like, assuming we have like, but subsets 2, 5, 6, the sum of XOR total for every subset of nums. Some or none. Yeah, the problematic part in this one is to generate all subsets, because we have permutation and combination. Yeah, okay, so if we had like bigger constraints, because we have in this case 12 numbers at most. So still it's a pretty big amount of combinations. So yeah, let's check the hints. Is there a way to iterate through all the subsets of the array? I mean, with a couple of for loops, sure we can. With 2 for loops, we can iterate through all subsets. Can we use recursion to efficiently iterate through all subsets? Can we use recursion? Let me think. I mean, yeah, kind of we can. So this feels more like a dynamic programming solution, where we'll generate all subsets. Though I'm a bit confused with the XORing part. Okay, so yeah, let's try to brainstorm a little bit on our whiteboard. Okay, so let's check one specific example. Let's try this one. So we have this example. Let me copy it. So I'll put it here. Okay, so if we try to dig into this problem, here we'll have like 5, 1, and 6. So how can we, using a recursion, how can we generate all possibilities? Yeah, let's try this. So how to generate all possibilities? So we may try to include the number 5, or we do not include number 5. So if we include number 5, then we go next to 1. So we may try to include 1, or we cannot include 1. If we do not include 1, then we'll include 6. If we go to 1, then we can have 6 remaining. So this will be the tree if we start with 5. So we'll have like 5, and then we'll have 5, 1, 5, 6, and 5, 1, 6. Okay. If we go with the next one, we do not include 5, so 5 will not be the start of our branching tree. Then we can have 2 options, to include or not to include, and then we'll have 6 only. So it will be this tree. And the last one will just include 6 as a as a, as an operator. So kind of we have this DFS structure, more or less. Kind of a Pascal triangle, but this is for trinomial. Yeah, here I'm trying to find a recursive way, a recursive function that will give us all possible combinations. So we can try another example. So here, how can I code this? Because we don't have 5. This is a trouble. If we go with this tree, so we'll have 5 XOR 0, it will be, where 5 itself, it will be 5. And then if we include 1, we'll have a 5 XOR 1. If we include 6, it will be 5 XOR 6. And if we go like next, 5 XOR 1 and XOR 6. So this will be like 5 sums. What we'll need to do is to sum everything together. So it will be like 5 plus 5 XOR 1, which looks like it's 4. 5 XOR 6 will be 3. Plus 516 will be 2. Yeah, this one. Plus we have 16 as well. So 1 XOR 6 will be 7. And the last one, 6. So this will be our sum. So how can we code this? That's the interesting part. Yeah. Because we can just use a couple of for loops to generate all possibilities, or we can try to use recursion in this case. So yeah, I'm interested into recursion. I think it will be a good exercise for me to train recursion, and maybe we'll get something cool out of it. Yeah. So we have this. Yeah, let me copy this part. I'll use my board here. So yeah, let's try this. So we'll need a struct solution. Let's try to add a couple of test cases. So we use test-driven development. Test solution, okay. So I have a couple of bindings to generate this. So let's use 1 3 5 1 6 and the last one. So let's start first with 1 3 1 3, and the output will be 6. Okay. And here subset XOR sum. So we have this first example. Yeah, let me add all of them. It will be easier. So 516 and this one. So let me copy those two. So this will be like 516, resulting in 28. And the last one, and this will be 480. Okay, so we reformat it a little bit. So yeah, first we do a to-do for this to compile. We run our tests, and obviously this will fail. And now we'll need our recursive call. Our recursive call. So probably we'll call it DFS. And we'll start at 0, because we'll need to start at 0. Yeah, so I'll create this function pubfn DFS. Usually I call them DFS because it's a depth search. We generate all possibilities. So in this case, we'll have a pointer. So it will be like the index number. So this will be an index of usize, and then we'll need the nums as well. So this will be a reference of a vec. Yeah, actually we can go with like this. So what's important for us? It's return this. Yeah, looks like I'll need to close this. A little bit too many notifications. So we have like nums. Now it's interesting for our recursive function. Because if it's a base case, but it's pretty much always a base case, what we'll need to do we need to figure it out how to include or not to include the item at the position at the current index. So to not include it, maybe we can do it like this. So let's assume we have like nums of index. Plus, so this is when we'll include it. So when we include this one, and we do an XOR of DFS of index plus 1. Let me think. But then if this goes out of bounds, if IDX is greater than nums len -1, we need something to remain the same. So if we go with this approach, yeah, so here we'll need to provide nums as well. But here we'll need to return something which will remain the same, will not change. So what XOR what will give the same number? I think it's 0. Maybe it's 0. So yeah, let me try. So let's put this return 0, and let's do a short test. XOR bots. So we'll have like let a equal print line. Just wanna see what this will return. So 15. So yeah, if we return 0 here, then what will happen? This means this goes out of bounds. And then we recursively use it, but it's not all the cases. Yeah, this is a bit more complex than I thought. But yeah, the base case for sure is this one. When we go out of bounds, we return 0, and we do this this part, like XORing this part, and then everything will go well. But we need to do a plus. So this is when we include it. But when we don't include it, yeah, I feel like we should have a plus part, but I don't. Oh, fine, yeah. IDX plus 1. So yeah. So this is when we include the current index, but this is when we don't include the current index and we go right away. So I have a feeling like this should be it. Looks like not. So we've got 6 instead of we've got 7 instead of 6. But why? Yeah, let's try to debug it a little bit and see. Is it correct? 6 should be 6. Yeah, should be 6. So we have like 1, 3, and 1, 3. But here probably we should have like nums as well. Yeah, let me check. So we have nums. This goes with the recursive part. Wait a second, what does this stuff? 14, it's a little bit too much. Yeah, let's try to use a specific example and debug it on our whiteboard and see maybe we can figure it out where our bug is. Yeah, probably I'll keep what I want to achieve is this stuff. But so this is our code, And now let's try to figure it out. What's the mistake? So we have like two numbers, 1 and 3. What we want to achieve, it's combination like 1, 3, and 1 and 3. But probably it will not be in this order. So it will be like 1, 1, 3, and 3. So if we go with the code, if we go with this code, we start at 0. Okay, so we start at 0. So nums of index will be 1. So we have 1 plus nums of index XOR the next number recursively. Oh, so we are counting it too many times. No, that's not right. That's not right, because the trouble is, yeah, you know what we can do actually? It's first sum separately, because my trouble is we included too many times. So yeah, first we will not need to do this anymore. So yeah, this stuff. Yeah, this should go. So here we have like, again, we try first approach. Nums of I, 0, so it will be 1. XOR DFS of next. DFS of next, of index plus 1. So index will become 1. Which will be 3. So it will be 3 XOR. So 1 XOR 3 XOR 0. So this will be like 1 XOR 3. I kind of forgot what's the value. It's 2. Okay, so this will be 2. XOR 0, it will be 2 again. So the first part of our recursion gives this. But the next part plus this. So we have index 0 at first, index plus 1, so it will be 1. So if you go here 1, yeah, kind of we get here, so it will be something like 1 XOR 0. So it should be 1. So it should be like 2 plus 1. That's interesting, because I'm not sure how do we get 7 here. Because if we do this code, we should receive like 3, I think. Or something is not right. But we received 7. Why do we receive 7? So if index is greater than nums len minus 1. Yeah, let's try to use the debugger. Keep it up, bro. Yeah, thank you. Thank you. So we are struggling to use recursion to generate all possibilities and doing the right XOR. So yeah, the recursion, it's tough. Okay, so let's use the debugger and see where is our mistake. Okay, so we have index 0, nums 1 and 3. That's right. So if index no, then we do nums of index XOR DFS of index plus 1 nums. Index is 1. Then we do nums of index 1, which will be 3. Index 2, we return 0. So we are right. But here it's 1. Index 0. Wait a second. I'm a little bit confused. Why did we enter here one more time? Wait. I think I have too many test cases. So yeah, let's comment the test cases for now. So first entrance, we enter here. So nums of index. We go recursively, executes this. No, we do this. He exits or exits. Okay. Then we do the second recursion. Yeah, that's insanely tough to debug. I mean, maybe recursion are cool, but I do not see the mistake though. That's the tricky part. I do not see the result expected, but the result is 7. How did you get 7? Yeah, I kind of will need to see the call stack if it's possible. Unfortunately, it doesn't show. So yeah, let's try to look at the call stack. Maybe this will give us a little bit more details. So we'll learn how to debug this stuff. So this is a process. Closure, yeah, that will be undebuggable. Yeah, so let's go slowly. Yeah, let's try this. So if we do this stuff, we'll do XOR or next. Or next, or next, or next, or next, or next, till we have all possibilities. So this, I assume the result should be like 3. Y2. Oh, yeah, 1 XOR 3, it's 2, correct. That's correct, okay. So we've got the case, but now we'll need to figure it out how to sum 1 plus 3. One plus 3. I guess the simplest way to do it's something like, I don't know, like nums iterator sum plus sum as I32. So we'll need to sum all numbers and then do the recursive part. So this should work for the first. Yeah, kind of we'll don't need this test. So the first test worked, but the second will not. No, because it's 14, but should be 28. Why? Because we have only this part. Yeah, this. Yeah, well, let me use new canvas. Take screenshot. We have this. So if we go now, what this stuff does for 5, 1, and 6, it just does this. XOR or everything. So we have 5, 1, and 6. So first we sum everything together. So it will be like 12. And 5, 1, and 6, if I look here, it's 2. So this equals to 2. So 12 plus 2 gives, or yeah, let's plus 2 equals 14. So this is why we got 14. But we need as well 5, 1 and 5, 6. So in this case, uh, 5, 1, 5, 6 and 1, 6. So we'll need these combinations. How can we achieve this? How can we achieve this? Yeah, man, that's tough. That's tough. So I guess, so yeah, kind of we need to do a num of index to include this, to include the number itself. Plus, we'll need to do a recursive call of nums of index XOR XORing the next part, the DFS I plus 1. And as well, if we don't include it, we'll need to count just DFS of I plus 1. So in this case, what we'll have here? We'll have 5. Then we'll do 5 XOR next one. So next one will be one of these two. So it will be 1. XOR 1. But actually it will not be like this. If we call it recursively, the formula will be, so yeah, kind of, yeah, let's use this color. So we'll start with 5. Then we'll have plus nums of index will be 5. Start XORing. We go DFS of I plus 1. So DFS of I plus 1. Here it will be 1, because we start again the same formula. It will be like 1 plus 1 XOR. We open again our formula, as we go recursively. That's actually the trick. So we go next. It will be like 6 plus 6. We open again, and here we'll have I plus 1, and we'll exit because it's 0. We exited this. Then here we'll do DFS of I plus 1. I kind of forgot already what's I at this level. Okay, so plus 0. We close this. Here we do again this. It will be like 6. Yeah, it's a little bit too many. It's a little bit too many. Oh my god. Imagine I receive this as an interview and I need to do it recursive. So yeah, that's done. I'm done. I would not figure it out. Yeah, but let's try. Let's try. Once again, what we want, we need 5, 5, 1, 5, 6, and 5, 1, 6. I guess here what we lack, we need some sort of maybe we should keep the structure. Yeah, maybe we should keep it in some sort of a vector. To have it something on those lines. So imagine we start. So yeah, let's start again. Yeah. So we have like 5, 1, 6. So we start recursively at position 0. So we start here, and in our solution we do not have anything. Then if we do not have in our solution anything, my DFS will have something like this. So it will be like DFS index nums and a solution argument. So here solution will start at some sort of an empty array at first, and if we start at 0, then we'll have 5 in our solution. So we can put we can put 5 in our solution. We're not 5. I mean, yeah. Okay, so if it's 0, so this is a kind of a base case. So if there is nothing in the solution, then we'll have just nums of I. So in this case, we'll have nums of I. So this is our starting point. Plus, and now we do the recursive call, where we have like a DFS, where we go to the next index. Yeah, I'll ignore nums for now because it's redundant. But in our solution, we'll have nums of I now. where we'll push nums of I, where here we can do like solution push nums I, and then here we'll send the solution. But at the same time, we need to go next to DFS and to not include this solution, e+1, and solution, which was prev solution. Prev solution. And here, we'll need to count in the solution. Yeah, we'll need to do the XOR operation. Yeah, so I kind of have an idea, though I'm not sure if we'll arrive anywhere. So let's try to code this. So this will be a mutable solution, which will be a vec of I32s. Okay, so here, if we have, let's try the base cases first. So if we have solution is empty, if solution is empty, we return but this solution is always empty. No, that's not the right case. I guess here we'll do XORing operation. So let result solution iterator fold 0. We'll do accumulator and item. So here accumulator XOR item. So item needs to be dereferenced. What's the problem? Oh, so we need to return the accumulator. Yeah. Okay, so we have the result where we do XORing. Next stage, what we'll be doing, we'll have like a solution. Okay, so we need to check if it's out of bounds. If IDX is greater than solution of len -1, return 0. So we need to check this, not solution, but nums. What's the problem? Yeah, we need to write more code. So to do. So here looks like it's a problem. Yeah, it's an immutable. Yeah, let's mutate it. Now we have this part. If it's out of bounds, but if it's not, then we'll do solution push nums of index. So we'll be pushing solution, and then we'll have the following. So we'll have nums of index plus result plus DFS included Yeah. Not yeah, so solution included will be solution. Yeah, I just need to copy it. So here solution included the push nums of index. So yeah, now we need to form the result. So nums plus index plus result plus TFS of index plus 1, because we need to go recursively. 1 with the solution included, nums, and 1 with solution not included. Oh my god, if this works, that will be insane. Yeah. So at first we have an empty vector. So here it's moved. Yeah, kind of here we'll need to send a mutable reference. Otherwise, this will not be possible. So we need to make it mute. Okay, so this is all ready. Yeah, kind of will need to clone this. And we need, yeah, we'll need to make it mutable. And we'll need to pass as a reference. I'm afraid to even run it, to be honest. Okay, so has overflow its stack. So it looks like we do not exit properly. Oh, so here it's not the index plus index, but the index plus 1. Okay, so first we got 8, but should be 6. Why? So let's check. So index 0. If it's index 0, I expect the result to be 0. Yeah, let's debug. So this stuff will be 0, that's right. This we clone, we push. So we have 1 plus 0 plus DFS of next with the 1 included plus DFS of next where we do not include 1. So okay. So I guess we go first. So solution is 1. Wait. Please go out. So result it's 1. Wait, but we do in this case then we double count 1. We don't need to double count 1. So it's just result. Yeah, let's run again. So we've got 1 in this case and 6. Why? Yeah, let's check again with the debugger. So it's 0. Okay. we push 1. It's 1. We have result 1 in this case. We don't need to exit. Solution included will be 3. And result is 1. And we go next. Wait, here, if we go out of bounds, we just need to return the result. Because it may happen that we go out of bounds, but still we need to compute the results of the things which we have. So it's 7 now. I don't think I'll... So we have an hour and 20 minutes on this problem. But yeah, it's interesting. If we'll figure it out, it'll be a very good exercise for us to train. So first, nothing. Result is nothing. Next, iteration result is 1. Solution it's this. So we have result 1 plus we go with 1 free. Or index 2. Okay, so here, okay, so result will be 2. Solution, it's no, because we exited. We just pushed the result. Okay, so we have like vec1. This part. So we go next, but how many times did we enter here? Because that's yeah, let me, yeah, probably here. Yeah, we counted multiple times though, that's not right. Yeah, probably another way is to just generate all possibilities and then do the counting. Yeah, let's try to generate all possibilities. Yeah, let's shift gears. We are shifting gears. We'll do all possibilities and then we will do the manipulation with the XORing part. So yeah, okay, so we'll still have the DFS part. DFS, we'll have our index. Yeah, index will remain. Have our nums, because we need the nums. We're gonna do without nums. But instead, we'll be returning a vector of I32s. And here combos. And let's assume we wrote the code for the combos part. Now we'll do like combos. We'll iterate each combo. We'll have a mapper. We'll have an x iterator fold. We'll do the similar thing which we did item accumulator equal item reference returning accumulator, and we sum everything together. So the assumption that our DFS will give us all the combos, the recursive function, and then we have the mapping part which sums everything. So now let's try to figure it out how we can write this. So we'll have like let mutable result. It'll be a vec. So we'll need to include nums of I. Result.push nums of I index. Then we'll do result. We'll need to concat it. But if I do it like this, so we'll have like vec. Yeah, I forgot how concat works. Not files. Rust concat vec. But yeah, I guess let's do differently. We'll still go with the solution vector. Vec of vex. Yeah, that would be mutable vec. Yeah, something like this. So for each solution, in our case, this will be different then. So let mutable combos will be vec nothing, and here we do mutable combos. Yeah, so this will not be like that anymore. And yeah, we'll need a nums, I guess. Let's switch the order of the parameters. What's the trouble? Oh, okay, so this will be like a vec of x. Okay, so here we'll have multiple solutions. So for each solution, we will need to clone it and then add the current index. So something like for a solution in solutions, let temp will be sol clone, temp.push nums of index, and here, yeah, here we'll need to do a boundary check above, and we'll need to here let level sols. And here we'll do how can cut works? It has a weird structure. Append A, extend B. Okay. Append. Okay, so append works for me. So it will be like sols append level sols. So this, it's not possible because we'll need to do this, and now it's possible. So we do append, and then what do we have? So yeah, let's check if index is greater than num/len. So in this case, we return back. Not back, sorry. What do we do? We just return len -1. Yeah, probably if index is less than nums.len -1. So we do this. Yeah, this makes more sense. Okay, yeah, let's try to run it and see what in the world did we get. Okay, so we've got our combos. Let's have a breakpoint here. Oh, yeah, kind of will need to include the starting point. So we'll need a base case in the form of if sols is empty. souls push vec nums of index. Not souls, yeah, but souls, solutions. Yeah, but yeah, again, we'll need to do some boundary checks. Okay, so we have one, not one. Yeah, this needs to be done at this level. And yeah, but we need to call it recursively. We didn't call it recursively. E plus 1 souls index plus 1 and nums. Okay, so we have this. So this doesn't work. We have this. So we have one vec with one solution. Okay, so we have this solution. Less or equal. Sorry, that's a bug. It was a small bug. Here we have this. We add second. We push this. We exit. We exit. We have 1, 1 and 3. Yeah, but we miss 3. Yeah, I guess this needs to be done in either case. Maybe. Okay, 1, go next. 3 and 3. Up, 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 up. Yeah. Yes, this. We copy this part. And we do it upwards here. Let's restart. Yeah, looks like I'll go with 2 pointers. Because okay, okay, good. Okay, good. 3, good. We don't go inside because it's out of bounds. Up. We have this, but I guess here we shouldn't append if we do not have anything. So if level souls empty, I guess it's not empty. Then we do this. So once more, let's check. Debug. Bam 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 bam. Empty, empty. Yeah, we kind of need to exit now. Yeah, probably if I'll do it here, if idx plus 1 is less than num/len minus 1. We go recursively if we have numbers. And we will not need this anymore. And this one as well will not need, because we will not call it if this is not needed. So yeah, let's check. Okay. We push. idx plus 1 is less or equal. Oh my god, every time same mistake. Okay, push, go next. Push, push, push. Go next, don't go next. Yeah, correct. So we have our solution 1, 1, 3, and 3. That's right. So we have the next one. So let's, yeah, the first one worked. So that's good news. So here we have 5, 5, 1, 1, 5, 6, 5, 1, 6, 1, 6, and 6. Oh my freaking god! Did we fix it? Did we fix it or not? Yeah, and it worked. So congratulations, we have 2 freaking tests done. Now, the question, can we optimize this? Can we optimize this to... yeah, first let's run all cases. Yeah, all cases works well. That's good. Oh, I'm thinking maybe I shouldn't store the solutions. Shouldn't store the solution, or should I? Okay. I mean, for now it's fine. Yeah, let's run. I just want to switch to another problem. Okay, so we don't need this. We need to pass this stuff. Yes, this solution subset. Yeah, that was a little bit trickier for a simple problem. So yeah, the tests are working fine here. Runtime, it's very bad. Memory as well. So yeah, let's... Oh, yeah, that's what I call a solution. And I don't even understand or an. And we shift. Yeah, this guy is genius. Oh my god, I'm not sure if I'll ever get to this level. So he shifts the bits on the right side. How many bits does he shift? Nums/len -1. So he doesn't or. Yeah, we kind of need to spend some time trying to figure it out. What in the world to get from this insanity? Yeah, probably that's a math problem. I guess that's a math trick. Because we generated all possibilities, but we don't necessarily need all possibilities. So, oh, yeah, tricky. Okay, yeah, I'm kind of spent 2 hours for one small problem, but yeah, we trained a little bit on. Yeah, let's try this this one. Sort by bits. You're given an integer array r. Sort the integers in the array in ascending order by the number of ones in the binary representation. And in case of 2 or more integers have the same number as ones, you have to sort them in ascending order. Okay. Okay. So there is a count once. There is a function called count once, which will give us the number of 1 bits in a number. So probably what we'll need to do is first create our vector. We can do something like a mutable with bits, and then we'll have array iterator map x, and then here we'll return a tuple x and x count once. X count once. So this will give us a tuple in the form of the number itself. So for example, 0 and 0 bits were ones and 1. Next, we'll need to, with bits sort by, I think it's that the function. I forgot a little bit on Rust sort by. A and B. Okay, so we have A and B. A and B or left and right. So left and right will be a tuple in our case. So left and right will be a tuple. So then we'll need to sort if left of 1 equal right of 1, then we'll do left of 0 compare right of 0. Probably here it will be a little bit more logic. Okay, else left of 1 compare right of 1. So we will sort it. And then we'll do with the bits, iterator map, and we'll get back our value, collect. So something on those lines, I think, should work. Wait. So sort by. Yeah. We need to close this. Yeah, I'm not sure I like the read box. I want to change the music. Yeah, I'll need to close that one. I don't like it. It's too dramatic. Yeah, this needs to be like that. Cannot be dereferenced. Okay, how about that? Okay, so we have no method named sort by found for. Oh, we need to collect this. Yeah. So we'll need to collect that. Let's arrange a little bit. Expected I32. Okay, that's easy to fix. And I guess that one is as well easy to fix. Awesome. So yeah, some problems we spend like 1 hour and a half. Other problems we spend like 5 minutes. So that's good. And looks like we have a pretty good result. Yeah, this one contains key. Yeah, a little bit more logic. So I like this one. So was fast. Counting bits. Given an integer n, return an array of n's of length n plus 1 such that I is the number of ones in the binary representation. It's very easy to come up with a solution with the runtime n log n. Why? Because we divide by 2. Okay, so n for each number in the numbers. Can you do it in a linear time, possibly in a single pass? Probably I can if I want to spend like 10 more hours. But simplest way, I guess, 0 and included. Yeah, included map x count once collect as I32 collect. So that would be n log n solution. Yeah, we'll think of a way to do it faster. Yeah, so that's a better solution. But yeah, I kind of tilted a little bit with the previous one. so want to go a little bit faster. The Hamming distance between two integers is the number of positions at which the corresponding bits are different. Given two integers, x and y, return the Hamming distance between them. So 1 and 4. Wait. Wait. So that's seems to be an easy one. Yeah, let's try to do some. Okay, so new canvas. So assuming we have the following numbers, so we have like 1 and 4. So 1 will be 0, 0, 0, 1, and 4 will be 0, 1, 0, 0. So if we compare bit by bit, Hamming distance. This feels like 3 and 1. Okay, so let's check. So here we can see, yeah, as from the example, here we have a difference in bits, and this one it's a difference in bits. So the question is, what exactly the Hamming distance between two integers is the number of positions at which the corresponding bits are different. Oh, so maybe what we can do actually, but wait, what will happen if we do XOR? Or 1, or not XOR but OR, X and Y, and then count once. Because if we have differences, then we do XOR and count how many ones we have. No, that's not right. Because we need differences, so we need yeah. Let's check once again what's the XOR. Every time I'm forgetting. Exclusive OR. XOR gate. So if 0 and 0, so if you have a difference, it's 1. Awesome. So this is what we need actually. So it's XOR. So we need to XOR every bit. But in our case, it will be like this stuff doesn't do anything. This stuff will be 1. This stuff is 0, and this stuff is 1. 0 actually. So 1, 0, 1. So 1 XOR 4 gives a number, which is this number, which is 5. And we count once in 5. And this will give us the resulting like 2. So that's the solution. Oh, pretty cool. So here, a simple solution will be like X exclusive OR Y. Result will count once, and as I32. And this should do the trick. Awesome. So yeah, we are getting somewhere. So what's the other solution? Yeah, exactly the same solution. So move on. Counting bits, having maximum strong pair XOR. Let's check this one. You're given a zero index integer enums. A pair of integer x and y is called a strong pair if it satisfies a condition. X minus y is less or equal than min x or y. Okay. So there are 11 strong pairs. 3 XOR 4. So we are playing with pairs. We are playing with pairs now. So not all possibilities, but pairs. All possible pairs. But actually duplicates are possible here. So I guess a naive approach would be to form all pairs, all strong pairs, and then do the max, do the XOR operation, and then the max part will be as well as my brute force solution pass. Yeah, so yeah, let's try to make first, in this case, what we can try to do. It's making the pass. So if we go on our whiteboard, so if you have a vector of 1, 3, 5, 6, if you have like 2 for loops for I 0 till n, so n equal 4 in this case, for I 0 n, and then for j from 0, because we need to allow duplicates, and a pair will be like ij, but we need to first identify if it's strong. If it's strong pair, then probably here we'll have a max XOR. So yeah, so usually we start like with a I32 min as a starting point. If it's strong pair, we do max and max and blah blah blah, and in the end we return max. So we need to write a function to identify if this is a strong pair. So yeah, let's try to code this. Strong pair pub, this kind of should be a private function. Fn is strong pair. X and X, which will be an I32, and Y an I32, and we'll return a Boolean. So we have the formula above. X minus Y dot abs less or equal than min xy. So we have the formula. Now we do our for loops. I in 0 nums len. Yeah, actually we can extract len. Nums len. And here we'll do for I len, for j in let pair or let x will be nums of I, let y will be nums of j. If guess we'll do solution is strong pair x and y. Yeah, we'll need our max. I forgot about it. Let max XOR. If we want to maximize something, we start with min. It's easier to handle, and this should be like immutable stuff. So max XOR will be max XOR max and x XOR y. And we should have max XOR. So I guess that should be the algorithm. Yeah, I have some typos. This one, for example. Looks like I've attempted too soon. Good. So yeah, we started to get some pretty good results. Yeah, this one it's a little bit faster. So yeah, with pairs, 2 for loops, and we are done. Okay, so we sorted this with Hamming, strong pairs. Let's try this one. Find the k-or of an array. What? The k-or of the nums is a non-negative integer that satisfies the following. The ith bit is set to k, or if and only if there is at least k elements of nums in which bit I is set. Okay, I think we are good. So I'm good for today. So we'll continue. So we'll have a part 2 session with the bits. We'll be continuing our journey with bit manipulation. So we learned a thing or two today. Oh yeah, still a lot of things to learn, but yeah, we spent a lot of time on the recursion problem to generate all possibilities. Finally, we did it, but took more energy than I planned to. So yeah, let's check the results for now. How many problems did we solve? So yeah, we did a couple of problems. I think I had like 97 or something, and we are now at 105. And overall 200 problems solved on LeetCode. So yeah, still a ton of work to be done, but we are grinding slowly. We'll get there. So thank you everyone to joining in, to be with me, to like, to comment. So it was a pleasant experience. So have a nice day, guys, and we'll have another stream during the week. Bye bye.